Good evening, and welcome to Perimeter's public lecture series here in the Mike Lazaridis Theatre of Ideas at Perimeter Institute for Theoretical Physics in Waterloo, Ontario, Canada. My name is Greg Dick. I'm the Director of Educational Outreach, and it is a pleasure to welcome everyone here this evening. Those of you here in the studio audience, those of you watching in the bistro, and those of you watching online around the planet. The lecture this evening, will last approximately 1 hour. It will be followed by question and answer. And if you're watching online, Dr. Damien Pope and a team of PI researchers are behind their keyboards ready to engage in conversation throughout the lecture. If you want to ask questions and engage that team, use hashtag #PILive. And also, if you do have a question that you would like me to ask the guest speaker, get that question in early through the hashtag #PILive so it makes it all the way to my phone. All right, and now it's my pleasure to introduce tonight's very special guest speaker, Dr. Rob Spekkens. Dr. Spekkens is one of Perimeter's own. He has been a faculty member here at Perimeter since 2008. His research examines the foundations of quantum theory. He received his BSc in Physics and Philosophy from McGill University and then completed his Master's and PhD in Physics at the University of Toronto. He held a postdoctoral fellowship here at Perimeter and then an International Royal Society Fellowship at the University of Cambridge. In 2012, he won first prize in Foundational Questions Institute Essay Contest. The title of his essay was Questioning the Foundations, Which of Our Assumptions Are Wrong? In 2015, Dr. Spekkens co-edited a book, Quantum Theory, Informational Foundations and Foils. And now, today, is the project leader of the international research collaboration, Quantum Causal Structures. Tonight, he will examine and explain why he believes many of today's quantum mysteries are actually the result of a category mistake concerning the nature of quantum states. Ladies and gentlemen, please welcome Dr. Rob Spekkens.
So I wanted to start the talk today by just making a few general comments about the process of doing science. In particular, I want to make an analogy between making scientific discoveries and solving puzzles. So I'm going to start with an example of a puzzle that you might be familiar, which is Sudoku. Maybe there's a few of you who aren't familiar with Sudoku, so let me just briefly tell you how it works. So you have this 9x9 grid of squares. Some of them are filled in with digits between 1 and 9, and your job is to fill in the blank squares with digits between 1 and 9, and you have to satisfy 3 constraints. Every row has to have each one of those digits appearing somewhere once, similarly for every column and for every 3x3 square. So over on the right here, I've got the solution to this particular Sudoku puzzle. And although it can be very hard to solve a Sudoku puzzle, once you've got the solution, it's very easy to test that you have got it right, because you can just verify that all the constraints are satisfied. And so science is often like this. So you have multiple constraints you have to satisfy that are competing with one another. So if you're doing physics and you're building on some pre-existing physical theory, then you have to, at least in your new theory, reproduce all the successes of the old theory in the domain where the old theory worked well. There are constraints coming from principles of rationality. You know, your theory should be logically consistent, it should be mathematically well-defined, those sorts of constraints. You have constraints where you want your theory to be coherent with nearby scientific disciplines. So if you're doing physics, you want it to cohere with chemistry and maybe with computer science. And then finally, there's the constraints that come from experiments, and you need your theory to reproduce the experimental data. But because how you interpret the data often depends on the theoretical framework of your theory. There is some give there. So maybe something that looks like an experimental disconfirmation of your theory ends up not being that if you interpret it appropriately. So there's some leeway in all these different constraints, and your job is to somehow make it all work and get a whole that satisfies all those constraints. So when you're in the midst of it, of course, it looks a little bit more like this. So clearly, whoever was doing this Sudoku puzzle got stuck at some point, and a lot of scientific progress is a bit like this. And usually the diagnosis is that it's somewhere along the way you've made a mistake, and that mistake is propagated forwards. You've done a lot of moves. What you've done seems internally coherent, but it's all based on this wrong foundation. And so at some point you get stuck and you can't make any further moves. And so in science, that happens as well. There's fields of science that are built on top of mistakes, and we need to correct those to make progress. But there's one kind of mistake that I want to focus in on, which is a category mistake. So this is a particularly egregious type of mistake where you're not just wrong about some entity in your theory, you're even wrong about what kind of entity it is. So this is a particularly bad thing to have happen to you, because it means that all the questions you ask about that entity are somehow wrong-headed, because you've got its nature wrong. Now, my favorite example of a category mistake that held back scientific progress is in the decipherment of Egyptian hieroglyphs. So Egyptian hieroglyphs are one of the oldest known writing systems. It's possible that they are the oldest writing system. They go back to at least 3000 BC. And they were used continuously for about 3,500 years. So the last person who could read and write in Egyptian hieroglyphs probably lived somewhere around 500 AD. It was only deciphered in the 19th century by a Frenchman, Jean-François Champollion. And so for 1,300 years, nobody could read hieroglyphs. All the inscriptions on tombs and on monuments were just silent. Nobody had any understanding of what this script meant. And so the question is, why couldn't we decipher hieroglyphs? And it turns out that when you look at the story, much of the effort towards decipherment was based on a fundamental mistake about the nature of a glyph. So there was an assumption that individual glyphs were ideograms, and that means they represent a concept directly. So that was the assumption. They don't depend on any spoken language. They just represent a concept directly, kind of like a sign at an airport where it's supposed to be a visual representation of some notion, and it doesn't matter what language you speak, you'll get the idea. So that was the assumption, that these were a kind of picture writing, and they had to figure out which concept was associated with which symbol to unravel the mystery. And it turned out, in fact, that the glyphs represented phonetic values, so things like consonant sounds, vowel sounds, syllable sounds, a completely different sort of thing to be representing. And so all the work that was done under the ideographic assumption really, in the end, didn't make much sense at all. Okay, so I'm going to come back to the story of decipherment later in the talk. But most of this talk is going to be about a different decipherment problem, which is deciphering quantum theory. So there, again, we have this very elaborate formalism, but there isn't agreement about what the quantum formalism says about the nature of reality. So there's lots of different ideas, disagreements among the experts, but no scientific consensus. So for example, you might have heard of some of these ideas. So one interpretation of formalism says that in certain sorts of experiments, cats can go into these strange states of being smeared out between alive and dead states, and it takes a conscious observer to open the box to collapse the cat back into a state of being alive or dead. And whether it's one or the other is completely indeterministic, and nothing in the world fixes which it's going to be. Another view is that actually everything is deterministic, but when you do a quantum measurement, the quantum state of the whole universe branches into two parts, and we have parallel worlds, and there's versions of all of us in a parallel world where the quantum measurement came out the other way, and we're all coexisting and evolving deterministically over time. Other approaches to quantum theory involve the notion that if I do a measurement on a particle here, it can happen that it influences the properties of some other particle far away and instantaneously. So this is sometimes called spooky action at a distance. This is also something that people say comes out of the formalism of quantum mechanics. And so the first thing I want to emphasize is that these ideas don't all live in a single interpretation of quantum mechanics. They're really competing ideas for how to make sense of quantum mechanics. They're alternative ideas of how to make sense of the nature of reality given the quantum formalism. I'm going to try to argue that the very fact that we don't have a scientific consensus on the right interpretation of quantum theory suggests that we haven't got it yet. So like the Sudoku puzzle, when it's complete, you can kind of recognize it's complete. That happens in science as well. When you've sort of managed to fit all the constraints of your scientific theory, it usually has the air of truth about it. So, for example, when Maxwell, who was thinking about electricity and magnetism, realized that his equations predicted electromagnetic waves that traveled at the speed of light, then he saw that all of optics was actually related to electricity and magnetism, and suddenly the entire theory of optics and the theory of electricity and magnetism mutually supported one another, and it was, everything was coherent and fit together, and it was so clearly right, and no scientist to this day has ever seen fit to go back to a time when we thought that optics was not an electromagnetic phenomenon. So the same thing is true here. I think there's some evidence that we haven't got it right simply because none of these pictures are so compelling that they've managed to achieve a scientific consensus that this is the appropriate way of going. So today I'm going to tell you a little bit about my own views about what is the correct direction to take for coming up with the interpretation of quantum theory. And I'm going to try to argue that it's not any of these things. All these various aspects I just told you about are not part of my preferred view. And furthermore, I'm going to try to argue that a lot of the strange features of some of these approaches, the fact that they don't cohere with one another and other physics, is a result of a category mistake. So I want to say that these are all like partially completed Sudoku puzzles where there's some mistake that's been made. And in this case, the mistake has to do with the nature of the quantum state. So the quantum state is really the central theoretical entity in quantum theory. It's usually denoted by the Greek letter psi. You don't need to know too much about what it is. But all the standard interpretations that you hear about all presume that the quantum state is a description of reality. So they presume that as I vary the parameters in the quantum state, I'm describing different universes. And I want to argue that, in fact, the quantum state is a very different sort of entity. It's describing a state of knowledge. So as I vary the parameters in the state, what's varying is they're really describing different statements about the relative likelihoods of various different realities. And you can imagine a variation in the quantum state while reality stays fixed. That variation just corresponds to a variation in our knowledge of reality. So two very different things, like the ideograms and the phonograms, being a state of reality and being a state of knowledge are two different, completely different things. Okay. I want to note that this problem of decipherment, scholars referred to that colloquially before it was deciphered as the riddle of the Sphinx. So I think it's sort of appropriate. There's a lot of analogies between the decipherment of Egyptian hieroglyphs and the problem of interpreting quantum theory. They're both very vexing, difficult problems. So I think it's kind of appropriate to think about the problem of interpreting quantum theory as a sort of modern-day version of a quantum-flavored version of the riddle of the Sphinx. All right, so let me get started with telling you a little bit about how quantum theory works. So for that, I'm going to consider a simple experiment. So what I have here is a pair of particles that get generated in the middle and taken away to labs. And then there's going to be measurements done on each of these particles. So over here on your left, you've got a measurement device. There's a little pointer. And for simplicity, I'm going to imagine there's only two possible outcomes of this measurement, which I'll call 0 and 1. X just labels the outcome. So X takes the value 0 or 1. Similarly, there's a little knob here, and that means you can do different kinds of measurements. So it doesn't really matter what these measurements are. They're measuring two different properties of this system that's coming in. And again, I'll just label those two settings 0 and 1. And I have the same thing over here on the right. I've got these binary outcome measurements with binary settings as well. And so what I can do is I can set this up, and I can choose a particular pair of settings, like take the case where they're both set to 0. And then I can push the button, generate one of these pairs of particles. In the quantum formalism, we describe them by an entangled state. I go off, I do the measurements, and I see what outcome I get. So in the first run, I might get the 0 and the 1 outcome, 0 for x, 1 for y. I do it again, I get the 1, 1 outcome. And I just keep doing it many, many times, and I calculate the relative frequencies of these outcomes. And in the long run, those can be interpreted as the probabilities for these 4 outcomes. And so in this case, for example, with 43% probability, I'm getting both 0. With 43% probability, they're both 1. And with 7% probability each, they're 0, 1, or 1, 0. And then I can go through and I can do that for all the other settings. So this is the kind of data you might get out of a quantum experiment. And it's a data table that you can show is predicted by quantum theory for a particular choice of the quantum state here at the center and for particular choices of measurements. So this is the kind of thing that quantum theory predicts. And the quantum state appears in the middle of that calculation. So one view is that, well, we'll just interpret the quantum state as a tool you use for calculating these probabilities, which is all you really care about anyhow, and that's it. That's its interpretation. Nothing about the properties of the particles or anything like that. So the first thing I want to do is tell you why I think that sort of approach to the interpretation of the quantum state is unsatisfactory. And so for that, I'm going to tell you about a paradox of classical statistics called Simpson's paradox. So the scenario is the following. You have a population of people who have some illness, and you want to test the effectiveness of some drug. So you find the subpopulation of these people who have taken the drug, and you just determine what fraction of them recovered from this illness. So you compute the probability of recovery given that they took the drug. And you look at the subpopulation that didn't take the drug, and you compute what fraction of them recovered. And in this case, it happens that the rate of recovery was greater for those who took the drug. So at this stage, you might say, well, it looks like maybe this drug is effective for this illness. But then you dig a bit deeper, and you look at the men, just the men. And then you notice that when you look at the subpopulation of men who didn't take the drug, the rate of recovery is higher than the population of men who took the drug. So it goes the other way relative to the full set. And then the real kicker is that when you look at the women, it goes the other way as well. So for the women as well, the rate of recovery was greater for those who didn't take the drug. And so this really seems like a paradox, because if you try to take a naive interpretation and just say, well, these conditional probabilities should be interpreted as the likelihood you'll recover in each of these various conditions, then it would seem that if you're a man, you shouldn't take the drug, and if you're a woman, you shouldn't take the drug. But if you're a member of the general population, you should. And that clearly doesn't make any sense at all. So if you haven't seen this paradox before, let me just persuade you that this can really happen by showing you a data table that achieves exactly these inequalities. So imagine that 300 men took the drug. That's the denominator here. And 180 of them recovered. You can compute that that's a 60% recovery rate. 100 men did not take the drug, 70 of those recovered. That's a 70% recovery rate. So sure enough, the rate of recovery for those who didn't take the drug is higher than for those who took the drug among the men. For the women, 100 took the drug, 20 recovered. 300 didn't take the drug, 90 of them recovered. So that's a 20% versus a 30% recovery rate. So again, we get the inequality here, which is that for the women, higher recovery rate among those who didn't take the drug. But now we take the totals. So if you ask how many people total took the drug, well, 300 men did, 100 women did. That's 400 total. And of them, 200 recovered. So that's a 50% recovery rate. Over here, it's also 400 total who didn't take the drug. But if I add up 70 and 90, it's just 160 who recovered. So the recovery rate's only 40% in that category. So sure enough, in the combined statistics, the probability of recovery is higher for those who took the drug. So this is very perplexing. To have a satisfactory resolution of this puzzle, you really need to be able to understand what's going on well enough to answer the question, what should I do? Should I take this drug or not, given this data? So first, I'm going to tell you how to resolve this paradox. First, let me tell you why it feels like a paradox, why we have intuitions that this doesn't make sense. And the reason is that we implicitly think that this is the causal structure. The resolution of the paradox has to do with causal relations among the variables. So we implicitly think that the causal structure must be something like this. So certainly treatment could have a causal influence on recovery, but also gender could have a causal influence on recovery because, maybe men are more likely to recover from this illness than women are, regardless of whether they took the drug. And if you think that this is the causal structure, then you really can't get the sorts of statistics that we have here. And the reason is that if this is the causal structure, then the probability of recovery when you take the drug is just the weighted sum of these two probabilities of recovery with the probabilities of being a man or being a woman. And so you would definitely have the inequality going the other way because it would just be the weighted sum of those two inequalities. So you definitely can't get these sorts of statistics if this is the causal structure. And the resolution of the paradox is that this is the causal structure. So it turns out this wasn't a fair drug trial where a coin was flipped to decide whether somebody got the drug or a placebo. It turns out that people got to choose whether they're going to take the drug or not. And if you look at the data, the men preferentially decided to take the drug, whereas the women preferentially decided to not take the drug. There was 300 men who took the drug and only 100 who didn't, and the opposite for the women. So in that situation, you now have an opportunity for treatment and recovery variables to be correlated even though treatment does not cause recovery, even though the drug does not cause recovery, because you have a common cause. The gender variable can act as a common cause. So here's what could be going on. It could be that men are more likely to recover from this illness than women are, regardless of whether they take the drug. Men are also more likely to take the drug. And so now you can reason as follows. If I tell you there's a member of the population, they took the drug, what do you think? Are they more likely to have recovered or not? And you can reason as follows. If they took the drug, they're more likely to have been a man. If they're a man, they're more likely to have recovered. So knowing that somebody took the drug is positive evidence that they recovered, even though the drug doesn't cause recovery. The only reason it's positive evidence is because there's a common cause on the two factors. So you have to disentangle the notions of causation and correlation to get to the bottom of this experiment. And so the answer in this question is that you should not take the drug because this correlation between treatment and recovery is just spurious. It's a result of this common cause, and the drug really isn't effective at all. Okay, so what's the lesson for quantum theory? Well, the lesson is just telling me what the statistics are in one of these experiments is not giving me an understanding of this experiment at the level of what causes what. Like in the Simpsons paradox, when you just gave me the statistics, there was more to be known. I couldn't answer questions like, should I take the drug or not? I needed to have a deeper analysis in terms of what the causal structure was. And so here we can ask, well, what's the causal explanation of why, for example, the variables x and y are correlated for certain values of s and t? Is it just that the particles, so from here on in I'm going to give the particles name, they'll be called A and B. Is it that the properties of the particles A and B are correlated because of some common cause, and then when I do measurements of the properties of A and B, those measurement outcomes become correlated because the particles are correlated? That would be one explanation of the correlations. Or maybe is it because that, as I choose the setting over on the left, for example, that has a causal influence on the properties of system B. Which setting I chose determines the properties, and that's part of the reason why the outcomes Y are correlated with the outcomes X. These are different kinds of causal explanations. The formalism of quantum theory on its own does not tell you what the right picture is. You need an interpretation of that formalism to answer questions like, is this going on or is that going on? So why is it important to have answers to those sorts of questions? Well, one reason is we now know that quantum theory provides advantages for certain applications like computing and cryptography. And we'd like to understand which sorts of tasks quantum computers can offer an advantage relative to classical computers. But when you're thinking about a quantum circuit or say a communication protocol or a cryptographic protocol, if you don't really understand what causes what and you just have access to the correlations, you're really at a disadvantage. Your intuitions are not solid about what you expect to happen. So if you want to be able to reason about quantum technologies, it's good to have a causal account. And secondly, perhaps more importantly, is that one of the big open problems in physics today is how can we unify quantum theory with our best theory of gravity, which is Einstein's theory of general relativity. And Einstein's theory is about space-time, which can change in response to matter, and that space-time encodes causal relations among events. So it's really a theory about causal structure. So if we can't even answer simple questions about what's going on causally in a very simple experiment on two particles in quantum mechanics, I think it's no wonder that we might have trouble understanding how to unify quantum mechanics with this theory that's all about causal structure. Okay, so it turns out that this question about, what's the causal account of what's going on in a quantum experiment is deeply connected to the question of how should we interpret the quantum state as either a state of reality or a state of knowledge. So let me say a few things about the quantum state and that distinction. So it's not going to be important for you to know that much about the mathematical details, but you need to know at least this, that a quantum state is something that's described by a number of real parameters. So if I take the absolute simplest quantum system, which is a two-level quantum system, we call it a qubit, the quantum state has 3 real parameters in it, the sums of their squares are 1, and I can think of it as a point on the surface of a sphere. These numbers would be its coordinates along these axes. But it's important here that this is an abstraction. Don't think of the quantum state as pointing in a direction in physical space. This is just to give you something about what the menu of possibilities for the quantum state are, but keep thinking of it as an abstract thing. The question is really, how should we interpret changes in the values of these parameters? What do changes in these values of these parameters represent? Are they changes in reality, or are they just changes in our knowledge of reality? So that's a bit of a subtle distinction. So let me give you a kind of little thought experiment to try to get clear on what that means. So here's how the thought experiment works. You've moved to Japan, and imagine that you don't read Japanese script. And every day you see this large billboard, the one in blue over here, and it has some numbers on it. You can read the numbers. And you notice that every day the numbers are changing, and you have no idea what it means. But you get it in your head after a while that this is probably something to do with the weather. So being a good scientist, you decide, I'm going to figure this out. You're not going to ask anyone what it means. You're just going to figure it out. So every day, you take note of what the numbers are. You do some measurements of the properties of the weather. And after a while, you figure out that that first number is the temperature on the day in degrees Celsius. And then sometime later, you work out that the second number is the wind speed in kilometers per hour. But even though you try very hard, you don't manage to figure out what the third number represents. You keep measuring more and more properties of the weather, and it seems like none of those properties match the value of that number. And so let's say you do this for 1,000 days, you're stuck, you can't make sense of this. So you try something different. You say, well, what if I look at the collection of days on which that number was, say, 0.5? And then you notice something, that out of that collection of days, in about half of them it rained. And then you look at the collection of days where the number was 0.75, and about 3/4 of them it rained. And you realize what that number represents is the weather forecaster's prediction about the probability of rain on that day. So this number represents nothing about the weather on the day itself, but a fact about what the weather forecaster thought the relative likelihood of 2 possible states of the weather, whether it's going to rain or not. And that's a very different kind of number. You won't find anything in the properties of the weather on that day that has the value of 0.5. So that's the kind of distinction we're talking about. Do the parameters in the quantum state represent facts about reality? Do their variation corresponds to variations in reality? Or should we think of them as representing relative likelihoods to various realities assigned by an agent? All right, well, let's go back to our quantum experiment. I need to tell you a couple of things about how the quantum state appears in the calculation of the correlations that we see in this experiment. So one way you could compute that data table we saw earlier is to use this fact about the quantum formalism, which is if you first take account of the setting you had on the left and the outcome you got, the quantum formalism tells you that if you, say, had the setting at 0 and you got the 0 outcome, the formalism tells you you should update your description of the quantum state of system B to some particular quantum state. So I'm going to just call it psi 0, 0, and imagine it's represented in this spherical representation as the arrow that points up. And for the other outcome, the x equal to 1 outcome, it tells you that it's going to be now represented by this quantum state psi 0, 1, and that corresponds to the arrow that points in the opposite direction on this sphere. If I do a different measurement on that left-hand particle, like that's the s equal to 1 setting, then for each of those outcomes, I get a different pair of quantum states that system B collapses to, which I'll just represent as this arrow pointing right and this arrow pointing left. So this is part of how the formalism of quantum mechanics work. And the question is, what picture of the causal structure of this experiment does this give me for each of the possible interpretations of the quantum state? So let's start with the idea that the quantum state represents reality. So I'm just going to use a very simple model where these 4 quantum states I told you about just correspond to 4 different physical states of that B particle. So imagine the B particle has some internal degree of freedom, some internal property, and it can really just be represented as, one of 4 possibilities, whatever they are. If you want, you could think of it as a ball that lives inside of one of 4 boxes or something like that. But it's just 4 possibilities. And now imagine that each of these 4 quantum states represents a distinct one of those 4 physical possibilities for particle B. Okay, so that means that when you do a measurement over on the left with, say, setting set at 0, and you get the 0 or the 1 outcome, then whatever the physical state of system B was initially, it transitions into one of these 2 physical states, depending on what outcome you got on the left-hand side. So it transitions in this way. And if you instead did setting 1 on the left, right, so you set the knob to 1 instead of 0, then the quantum formalism says, if you interpret the quantum states as describing reality, that's going to transition, whatever it started as, it's going to transition into one of these other 2 states. So notice that the first pair of states correspond to sort of being in one of the back 2 boxes here. The second pair of states corresponds to being in one of the front 2 boxes. They're mutually exclusive possibilities. And that means that what you choose for the setting over on the left will influence which menu of possibilities B is going to end up in. Is the physical state of B selected from, the menu wherein it's in one of the back 2 boxes, or is it selected from the menu where it's in one of the front 2 boxes? You don't get to choose which of these 2 occurs. That's random. You just get an outcome here, which determines which it is. But what you do get to choose is that setting, and that determines whether it's in one of the back or one of the front. And that means that your choice of that knob setting has influenced the physical state of B in a non-trivial way. It can only be in one of these 2 possibilities if it was set at 1, and it can only be in one of the other 2 if it was set at 0. So it means that the setting variable has had a causal influence on the physical state of system B under this interpretation. So this is like the case in the drug trial where the treatment has a causal influence on recovery. Okay, so let me notice something that's a little bit uncomfortable about this approach, which is that Einstein's theory of relativity says that there's a fundamental limit on how fast any causal influence can propagate, and that's the speed of light. And it turns out that I can set up this experiment in a way that the choice of which setting is made here is made at random at the last minute, and this other measurement is done so far away that even after this choice is made, if a signal goes out at the speed of light, it doesn't get here in time before this guy has to report an outcome. And so if this causal influence were propagating at the speed of light, it couldn't change the properties of system B in time before B was subjected to this measurement. And therefore, if I'm going to imagine that this is what's going on, I have to imagine that these causal influences are propagating faster than the speed of light. And that's in tension with Einstein's theory of relativity, and that's why people call this spooky action at a distance. So some people have an idea that maybe this causal influence doesn't even propagate through space-time at all. Maybe it just sort of jumps over space-time and immediately has an influence on the other particle far away, instantaneously. It's also spooky in another respect, which is that you might have expected that if you've got a causal influence that's running from the left over to the right particle, that you could use that to do things like send messages faster than the speed of light, set up a telephone line that you wouldn't have to wait for light to arrive. But it turns out the quantum formalism says that's not possible, that the statistics of the outcomes here, so the values of y, the different probabilities for the value y, are independent of how you set the knob over on the left. So that's also quite spooky. You've got this causal influence there, and yet you can't use it to send signals. Okay, so that's what happens if you take this view, that quantum states represent reality. Now, what about the other view? What if you take the view that instead they represent just our knowledge of reality. Well, then for these different vectors here, I'm just going to represent them again. I'm going to imagine that this particle B just has 4 physical states, and these 4 quantum states I'm going to represent it by a distribution, a probability distribution now, where I say, well, I know it's not in one of the front 2 boxes, and it's equally likely to be in one of the back 2 boxes. And for this one, I'll interpret it as being equally likely to be in one of the front 2 boxes, but definitely not in one of the back 2 boxes. And for these 2, it's definitely on the left, definitely on the right, but we don't know whether it's in the front or the back. So say you take that view, then you interpret this same experiment in a very different way. You say, well, my choice of what to measure over here, and I can choose the setting 0, get outcomes 0, 1, that just determines how I update my beliefs about the particle B. So I update, whatever I believed about particle B initially, maybe I had no information about what its physical state was, I'm going to update my beliefs to being it's definitely in one of the back options if the outcome was 0, and it's definitely in one of the front options if the outcome was 1. But if I'm doing the other setting, the 1 setting, then I update my beliefs differently. I update to one of the left options or one of the right options, depending on the outcome. So all that's happening as I register the outcome over here is I'm learning how I'm going to refine my knowledge. Am I going to learn about this back-front degree of freedom, or am I going to learn about this right-left degree of freedom? I get to choose which sorts of properties of A I'm going to learn about. The properties of A are correlated with the properties of B, so what I measure on A will determine what I can learn about B. And here I'm just sort of learning 2 different kinds of properties about B, depending on what setting I chose. But all along, system B can be in some fixed physical state. So maybe it's, for example, in the back left-hand corner. And then if that's the case, then if I choose to measure the 0 setting, I'll get the 0 outcome, and I'll refine my information from knowing nothing about where it is to knowing that it's in one of the back 2. Or if I choose to measure the other possibility, I'll refine my information from knowing nothing to knowing it's one of the left ones. But all along, it's just been in that back corner, and nothing I've chosen over on the left is influencing or changing its physical state. Its physical state is staying the same. All that's changing is my description of what I know about that physical state. What are the options that seem possible relative to what I've learned? Okay. So in this case, this is clearly like the drug trial where the treatment simply informs you about the recovery variable by virtue of some common cause acting on the 2. So here, the properties of A and B are correlated by virtue of a common cause. And the reason, learning X teaches me something about B and Y is because of that common cause. But there's no influence. Good. This experiment I've just told you about was actually proposed by Einstein in a very famous paper that he co-authored with Podolsky and Rosen. And the point of that paper was that Einstein wanted to point out that if you take the view that the quantum state describes reality, then you're forced to this uncomfortable conclusion that there's going to be these spooky action at a distance. He coined that term, and it was basically a criticism of that idea. He thought, this is inconsistent with the principle of relativity, and therefore we should dismiss this idea. The paper itself wasn't written by Einstein. Scholars think it was written by Podolsky. And if you read Einstein's correspondence from that period, he actually confides to his correspondents that he didn't quite like the way the paper turned out. And he said, look, the main point I was trying to make was kind of lost, so let me make it for you. And so if you read that correspondence, you'll see that the point he was really trying to make was that the quantum state should be interpreted as a state of knowledge. So here's a quote from one of his papers. So he says, Psi 2, that's what we would have called the quantum state of system B. Psi 2 does not describe the totality of what really pertains to the partial system 2, rather only what we know about it in this particular case. And in another letter he writes, I incline to the opinion that the wave function, which is another way of saying the quantum state, does not completely describe what is real, but only maximal knowledge regarding that which really exists. Okay, so it's very clearly this notion that maybe the quantum state is just describing what we know. So that was 1935, and since then, I would say there's been a lot of progress on the question of whether we can really make sense of quantum theory in this way as a state of knowledge. So I'm not going to tell you about the whole history of that project, but let me just mention one thing. We now know that there are certain parts of quantum theory where we really can interpret the entire formalism in a way where quantum states really are just conventional states of knowledge, meaning probability distributions over some set of physical states, exactly the kind of way I showed you. So I'm calling these the Clifford fragments of quantum theory. So the idea is that quantum theory allows for a given type of system all sorts of different preparations you could do on it, all sorts of different measurements you could do on it, transformations, and these fragments just look at a subset of those. They say consider only a subset of the states and a subset of the measurements and the transformations, and it's still a very rich theory because I can compose that subset in any way I like, but I never get out of that subset. But the interesting thing is that although they're in some sense a small part of quantum theory, they already contain all the sorts of mysterious quantum phenomena that you might have heard of, like entangled states, this remote collapse of the wave function we've just been talking about, this idea of a superposition principle, interference phenomena, teleportation, something called the no-cloning theorem, wave-particle duality, and the list goes on and on. They're all in there in those kinds of theories. And so the fact that in those kinds of theories we can clearly interpret the quantum state as a state of knowledge means that all these kinds of phenomena can be understood very naturally under this point of view. They appear a lot less mysterious than alternative interpretations wherein the quantum state is represented as a state of reality. So let me tell you a little bit about what those Clifford fragments of quantum theory look like. I'm going to actually tell you about one for which you don't have a precise representation in terms of probability distributions. Others you do. Most of them you do have a precise representation. It's just that this one's really the easiest one to explain, so I'm going to focus on this one. So it applies to collections of these two-level systems, collections of qubits. And if I just look at one qubit, it says that out of all these different directions the arrow could point, you've only got these 6 directions, all the poles of that sphere. These are the only 6 states that appear in the fragment of that theory. And the formalism says that a pair of these that point in opposite directions, they correspond to a measurement you could do. So there's 3 possible measurements you can do on this qubit. And then the transformations correspond to rotations that keep you within this set. And so that's the set for one qubit. If you look at a pair of qubits, now you've got some states, quantum states that are a fixed vector for each qubit. So the vector could point up for both. It could point down for both. But you also get these funny new possibilities, the entangled states, which are a kind of sum in the space in which the higher dimensional space in which these vectors live, of options like both up and both down. Those, so there's many more states than these. I can do all the rotations on the individual ones. There's extra transformations I can do on the pair. There's sets of measurements, but there's a finite number. You can work them all out. You can figure it out for 3 qubits, any number of qubits. And it's called a Clifford theory because the transformations are associated with something called the Clifford group. And so these theories actually have been well studied in the context of quantum information theory, where they're relevant for quantum computation, in particular quantum error correction. So it turns out that if you represent these different quantum states by probability distributions, you can reproduce the operational predictions. There's a caveat, but for the purpose of this talk, let's just say you can reproduce them. And the model is exactly the one I was showing you earlier. You imagine that this qubit really just has one of 4 possible physical states, and these 6 different quantum states just correspond to uniform distributions over 2 out of those 4 physical states. And when you move to pairs of these qubits, now it's a little bit trickier to represent as distributions, but the way I'm going to do it is that particle A has one of 4 possible physical states. Particle B also has one of 4 possible physical states. If we number these guys as, say, 1, 2, 3, 4, and I lay them out along a line, 1, 2, 3, 4, then this state of knowledge just corresponds to knowing that the first bit is either in the 1 or the 2 state, and knowing that the second one is in the 1 or the 2 state. So my knowledge is just a uniform distribution over these 4 guys. So this is like they're both in the 1 state. A is in the 1 state. A is in the 2 state. B is in the 1 state. A is in the 1 state. B is in the 2 state, and they're both in the 2 state. So you just know that it's one of those 4 possibilities. And similarly, for this guy, you just know that it's one of these four. And then these entangled states end up being a very particular kind of state of knowledge where you know nothing about the physical state of each individual particle, right? So you don't know whether it's 1, 2, 3, or 4 here or here. But you know that whatever the A particle, the B particle is in the same physical state. So they're either both in the 1 state, or both in the 2 state, or both in the 3, or both in the 4. So that's the kind of knowledge that corresponds to this quantum state in this model. It's a state of knowledge where you know everything about the relationship between the two particles and nothing about the properties of the individual particles themselves. So the way that this stuff usually gets represented in papers is with these sorts of diagrams where I just color in 2 out of the 4 boxes to represent the ones where there's a non-zero probability. The measurements are just a partitioning of the boxes into the 2 options. So, for example, if I've prepared the quantum state corresponding to this distribution and I do this measurement, it just says, well, if the physical state is up here, then you'll get the first outcome. And that happens half the time. And if the physical state is on the bottom, you'll get the second outcome. And this just says that there's probability half for each. So it reproduces the operational statistics of this theory in this very simple way. And this is what the kind of thing it looks like for 2 systems, where you got all these possible states of knowledge, all these possible measurements, which are partitionings of these 16 physical states into 4 sets of 4. And you'll notice that what this theory exhibits is that all your states of knowledge are incomplete knowledge. You never learn exactly what the physical state is. You only ever get partial information about the physical state. Here as well. And so that's the sense in which it's very much like Plato's allegory of the cave, where he imagines prisoners in a cave that only see the 2-dimensional shadows of some 3-dimensional objects behind them. So in this approach to quantum theory, you can never know everything about the physical state of the particle, but you can learn different aspects of it. You can ask, is it in the back or the front, the left or the right? Those are like different kinds of angles at which you could project the shadows. And in fact, you can derive this Clifford fragment of quantum theory just from this assumption that there is a restriction on how much you know. You can only ever know half of the facts about the system. Okay, so anyways, that gives you a bit of a flavor for how this model of the Clifford fragment looks. And I just wanted to mention that it's extremely simple, right? It's not much more complicated than what I've told you. So anyone could really sort of understand how this works. And, as a parent, you always want to give your kids a leg up in the world. So I thought I could teach my son a little bit about this model of quantum theory, and he might be, ahead of the game in understanding quantum theory. So he's 3 years old right now, and I know what you're thinking. I've left it kind of late. But actually, I got started a couple of years ago, so I actually didn't leave it late. And I'm just going to show you a photo of his first lesson about this theory. There he is. And I think it's pretty clear if you look at it on his face. First of all, he's clearly getting it. But second of all, I think it's clear that he's warming to the idea that quantum states are, in fact, states of knowledge. And it's important to understand that early on. Good. So, so what's the situation? We have this part of quantum theory where we can unambiguously say quantum states can be represented as states of knowledge. It reproduces a whole bunch of the things that we usually take to be mysterious about quantum mechanics. However, not all quantum phenomena live in those sorts of theories. There are some notable exceptions. So something called Bell's theorem, the Cauchy-Specker theorem, the fact that quantum computers do better than classical computers. These all require you to be in the rest of quantum theory, in a broader theory. So the question remains, can you pull off an interpretation of the quantum state as a state of knowledge over here in the rest of quantum theory? And I'm going to give you an idea of why that's challenging by telling you a little bit about Bell's theorem. So this is a theorem from 1964 by the Irish physicist John Bell. And it uses exactly the same experimental setup that we saw for this Einstein-Podolsky-Rosen example. And all they did was they allowed for different sorts of measurements. So the kinds of measurements that Einstein, Podolsky, and Rosen considered could really be thought of as living in one of those Clifford fragments, whereas Bell considered more general ones. And he showed that you can, quantum theory predicts you can get the kind of data table that we saw earlier on in the talk. And then he was able to prove that if you think of the quantum state as just a probability distribution over some underlying physical state, and this being the causal structure, there's no way to explain these kinds of correlations. So you cannot imagine that what's going on when you're updating the quantum state of system B is just one of these sorts of refinements of your information about the physical state of B. And so many people see that result and they think, oh, so that shows that there is this spooky action at a distance. We can't think of quantum states as states of knowledge, so we have to go one of these other routes. Perhaps we may as well grant that the quantum state is real. But I want to argue that there are some other options here, because it's not necessarily the case that the only way to represent a state of knowledge is using the formalism of classical probability theory. It could be that, so we normally think about mathematical formalism in physics describing physical theories, describing reality, but there's a whole mathematical formalism associated to making inferences in the presence of incomplete information. So that goes by the name of probability theory or the theory of Bayesian inference. And it could be that that's wrong, that in fact, when we want to reason about quantum particles, the reality of a quantum particle, first of all, is not described simply by some variable that takes one of a set of values. It's somehow more exotic than that. But more importantly, perhaps when we want to describe our incomplete information about the reality of that particle, we don't use classical probability theory. We have to use something more exotic, more general. We have to use a new kind of theory of inference. So let me give you an idea for what that might look like. So same experimental setup again. Let's just go through how we would update our information about this variable, B, this particle B over here, given some new information about what the outcome is on the left. How would the normal formalism for reasoning under uncertainty work? Well, when you learn the values of S and X, it tells you should take whatever you use to describe your initial information about B, some probability distribution over B, and update it to what's called a conditional probability distribution. So it's a new distribution like the types we were seeing, conditioned on the values of S and X. But note that what you know in the problem, you're not given this immediately. The kinds of things you know about the problem is, I've got this device, it prepares a joint distribution on the variables A and B, and I've got this measurement device which tells me a conditional, x given as. So it says for a given physical state of A and a given setting value, it predicts what the probabilities of the different values of x would be. So that's what's given in the problem, but this is what I need to figure out. And so the formalism of classical probability theory tells you how to do that. So I'm going to give some equations now, but it doesn't really matter what the form of the equations is. It'll just give you the flavor. So the first thing I want to do is a step called Bayesian inversion. So I'm given this information about what A and S teach me about x, but what I'd like to know is what do x and s teach me about A? So I want to compute this conditional probability, A given s and x. This is the formula that allows me to do it. Everything on the right-hand side here can be expressed in terms of what's given in the problem. In the next step, I take that joint distribution over A and B, and I compute from it this conditional, which tells me what I learn about B when I get new information about A. That's this guy here. So now I want to combine what I learn about A given x and s and what I learn about B given A to what I learn about B when I learn X and S, the thing that I'm interested in. And there's a formula for that, which is just called the belief propagation formula that combines these two conditionals, sums over A. So there's this whole framework, this calculus for how you ought to make inferences, involves taking products of probabilities. So the idea here is that that's what has to change. When we think of this rule wherein the quantum state of B updates to psi of B given Sx, so conditioned on certain values of S and X, we should just think of that as the same sort of thing as what's going on here, but in a more general setting. But it's not enough to just sort of decree that that's how we should think about it. You need to show that you really have a formalism that allows that to work. So what you're given is this entangled state on A and B. You're given a characterization of your measurement over on the left, and I'm just going to write that as a conditional quantum state. So this is work with a colleague of mine by the name of Matt Leifer. So we introduced, it doesn't really matter what formally how we represent these things, but you have representations, analogs of these conditional probabilities. And then you can show that there are indeed analogs of all these different sorts of formulas for Bayesian inversion, for computing conditionals, and for propagating your beliefs. And there's a certain kind of mathematical product that you need to make it work, a certain kind of analog of that sum operation. But those details aren't really important. The point is that it is conceivable that our best theory of how to make inferences in the presence of uncertainty is not classical probability theory, that we need to replace it with something else. And if you do the calculation, you update your beliefs about B using this formalism, and you compute the correlations, what you can learn about Y given X, you'll get exactly the quantum result. So that's what we were able to show, that we can reproduce the statistics, even in that Bell experiment, while simultaneously thinking of the process, that remote collapse process, as a pure Bayesian updating, a pure refinement of your information. The problem is that although we succeeded for this sort of experiment, we haven't got a formalism that'll work on any experiment you give me. So that's an open problem. How can you make this work for quantum theory generally? We don't know how to do that yet. Okay, so we know that quantum states can be understood as conventional states of knowledge in these Clifford fragments. We have some ideas for how they might be understood as more exotic kinds of states of knowledge in the rest of quantum theory, but there's work to be done here still. So let's get back to hieroglyphs. What does this have to do with hieroglyphs? What's the analogy between this category mistake that I'm talking about and the category mistake here? I mentioned that it was around 500 BC where a hieroglyph stopped being used. In the Renaissance, people discovered a book that was written by a Greek scholar by the name of Heropolo, who lived around 500 BC. So Heropolo was trying to make sense of hieroglyphs. He was very close in time to people who actually knew hieroglyphs. But nonetheless, Heropolo didn't know how to read hieroglyphs. And he decided that they were ideograms, that they represented concepts, and he tried to make sense of hieroglyphs using that approach. And all the scholars in the 16th and 17th and 18th century basically followed Heropolo's idea that these were ideograms. For example, he would say things like, the symbol of a hawk, well, that represents the notion of swiftness, or, a crocodile might represent the notion of evil. Now, some of these, the values he got happened to be right, because he was living so close in time to people who actually knew these things. So, for example, the goose, he thought represented the notion of a child, and he was sort of right. So, in retrospect, we now know that the goose symbol represents a phonetic value, the sound sa. And sa, in the language spoken by the ancient Egyptians, was the word for child. And so that's how goose managed to represent the word child. But it also was the word for goose. So it was in that language, it was a homophone. It was these two words had different meanings, but they sounded the same. So it would be very convenient then in your script to use an image of the concrete thing, the goose, to represent both the goose and the child, which sound the same in that language. It's the sound of the language that the goose is representing. So Heropolo didn't know that, and he just made up a story about why goose represents child and said, well, it's because geese are particularly protective of their children, so when you see an image of a goose, you clearly think immediately about a child. So he decided he was going to decipher or try to decipher hieroglyphs under this ideographic notion. And if you go through his book, you'll find he looks at certain combinations of symbols and comes up with meanings for them, and they're very bizarre in some cases. I like this last one here. It's just a few symbols which ends up representing a man who has been succeeded in his property by a son whom he hated. And I just think about, if I got that in Pictionary, what would you draw to try to represent that concept? It's kind of remarkable if a few symbols can represent it. And so, after the Renaissance, people followed in that tradition. So there was a scholar by the name of Kircher who tried to interpret hieroglyphs in terms of ideograms. So there's this nice obelisk on the island of Philae. And Kircher deciphered one of these inscriptions. This is just an excerpt from that decipherment, but it's really unclear what it means. The beneficent generative force commanding through supernal and infernal dominion augments the flow of sacred humors emanating from above. It was a very uncontrolled sort of game, clearly, the attempts to make sense of these hieroglyphs. And that's basically how it stood for a long time, until 1799, and that's the year where Napoleon army invaded Egypt, and French soldiers discovered the Rosetta Stone. So the Rosetta Stone had a decree inscribed on it in 3 different scripts. So the bottom script was Greek, with the Greek phonetic alphabet. And the Greek language had persisted into modern times, so people knew how to read the script, so they knew exactly what this edict said because they could interpret the bottom. And they knew that these other 2 scripts said exactly the same thing. And the top script was Egyptian hieroglyphs. The middle script is called Demotic, and it turns out we now know that it's sort of a cursive later form of the hieroglyphs. But this is very much like the quantum situation. I mean, after the Rosetta Stone, this particular bit of hieroglyphs, you know exactly what it says. There's no ambiguity about that. And the question is, how does it manage to say that? And that's very similar to what we have in quantum theory. We know what the correlations are going to be, but how does quantum theory end up generating those correlations? What's the causal story behind the generation of those correlations? That's what we really want to know. Okay, so I mentioned that the guy who ended up deciphering this was Champollion. So he got interested in the problem at a very young age. He got a copy, a high-quality copy of the Rosetta Stone in about 1808, and he got to work on it. And he inherited ideas from other scholars at the same time who were working on the problem. And one of those ideas was that there was these special parts in the hieroglyphs that were circled, and the French soldiers called them cartouches because they resembled the bullets. And the idea was that the cartouches contained names of pharaohs. So in the Greek text on the Rosetta Stone, the name of Ptolemy appeared many times, and there was a number of cartouches in the hieroglyphs. So people had the idea that this must somehow represent the name of Ptolemy. And they had ideas about what the phonetic values of some of these symbols might be. And Champollion looked at some other hieroglyphs where there were cartouches, which he was confident represented the name of Cleopatra. And then he could sort of figure out that some of these symbols must have certain phonetic values, like the square must represent the P in Ptolemy and Cleopatra, and the line must represent L. And he started figuring out what the phonetic values of these different glyphs were, and he was looking at more and more cartouches, and suddenly he saw names of all sorts, even in the more ancient hieroglyphs, names of ancient pharaohs that we know. And so it became very clear he had a good table of phonetic values for these glyphs that appear in the cartouches, but he didn't have a decipherment of hieroglyphs because he was so wedded to the idea, this ideographic fallacy, that he couldn't bring himself to imagine that the rest of the hieroglyphs should also be interpreted phonetically. He thought it was just the cartouches that had to be interpreted phonetically, and he had a kind of rationale for that. He said, well, a pharaoh's name, that's a proper name. Some of them were, foreign, so you would be forced to spell out those names phonetically rather than have dedicated symbols for them. So it's fine if the pharaoh's names are phonetic, but everything else are still ideographic. And so he worked on this. It's 1822, so he's been working on this for a while, and he's worried about his competitors scooping him. So he's not sleeping much, he's hardly eating, he's just working day and night on this problem, not making much headway. And then finally he decides one day that he's going to take this idea that the glyphs represent phonetic values and cast his view to the rest of the stuff outside the cartouches and see what happens if he thinks of it phonetically. And suddenly he starts seeing the sounds and the grammar of a language he recognizes, the Coptic language. So it turns out that the ancient Egyptian language survived to modern day in the Coptic liturgical tradition of the Coptic Christian Church. And it happened that Champollion had studied Coptic and the grammar of Coptic, so he could recognize it. And so he suddenly realized that all this script was a phonetic rendering of the language of Coptic. And he had it. That was the eureka moment. So he ran across town to where his brother worked. He burst in and he shouted, "Je tiens l'affaire!" And then he collapsed on the ground and was sick for about a week. He was just exhausted. But when he finally recovered, he wrote it up, and the scientific community realized that his phonetic decipherment really stood up to scrutiny. It made sense of a lot of disparate facts. It was very coherent. So, for example, this obelisk on the island of Philae, the cartouches here just get interpreted according to his decipherment as the name of the Caesar Domitian, who was indeed the Caesar in the Roman Empire at the time that this obelisk would have been erected. And it all makes sense, and it's like the completed Sudoku puzzle. No one would now go back to the idea that glyphs could represent ideograms. Okay, so what's the point? Well, this idea, this category mistake, the idea that hieroglyphs are ideograms, led to interpretations of hieroglyphic writing that were somewhat bizarre, but more importantly, they didn't really cohere with other facts, facts about archaeology and the language that was spoken by the ancient Egyptians, and what the Egyptians would likely have wanted to write on various monuments. They sort of stood alone and did not have the character of a real understanding of hieroglyphs. And I want to argue, and I have argued, that the idea that quantum states represent reality lead to various interpretation of quantum mechanics that are clearly not as ridiculous as any of this by a long shot, but they do have some problems. They do have certain incoherences in them. And so in particular, the idea that there is spooky action at a distance is clearly in tension with the theory of relativity. So I think there are good reasons to think that something is wrong with these interpretations. And now, I've told you how, in hieroglyphs, it was a two-stage revelation. First, there was the recognition that the cartouches must be understood phonetically, and it was only later that it became clear that you could understand all of it phonetically. And there's something similar for this hypothesis that quantum states are states of knowledge. We know that there's these particular fragments of quantum theory, the Clifford fragments, where we can really pull this off with just a totally conventional notion of a state of knowledge. We can really represent quantum states as states of knowledge there. And we have some ideas for how to do it in the rest of the quantum formalism, but that is still an open research project, and all I can say is that I am enthusiastic about its prospects. So with that, I'll end. So thanks very much.
You get to go to center stage. All right. We'll open the floor to questions. So there's a microphone right here. If you have a question, you can make your way there. And I can start with an online question. And it's spooky action at a distance. Here's the question. Is spooky not the right word to describe action at a distance? If you could choose a better word than spooky, what would it be?
Oh, good question. I would choose the term fine-tuned. So I mentioned that one aspect of the spookiness was that although you have these causal influences that are propagating superluminally, you can't use them to send signals. And one way to express that conflict is to say that if I try to write a model that has both those features, causal influences but no signals, it'll turn out that, so in this model, the variable b over here is going to depend on its causal parents. And generally, we allow any sort of conditional probability to describe that dependence. But if I want to make sure that you can't send signals, then out of all the possibilities for what that conditional probability might be, there's only a very small set that ensure that I can't send signals. And so out of all the possibilities for the values of the parameters in the model, there's only this very precise set of possibilities that will achieve these two facts. And so you could say, well, that's a very fine-tuned model if it has those features.
All right. I'm going to ask a question because it popped into my head. So I get to see the courageousness of scientists all the time. You said Bell ruled out conventional thought, the idea that the state of knowledge wasn't the right way to go. And yet, here you are, not in the 60s, in the 2000s, diving into it. What gave you the courage to follow that path?
So maybe I could say a couple of things about how I ended up working on the foundations of quantum theory. So when I was doing my undergrad, I learned that I could do a joint degree in physics and philosophy, and that really appealed to me. So I started doing that. And it was only in the philosophy courses that I started hearing about the interpretational problems of quantum theory. And that really interested me, but at the time it was very difficult to pursue a career in physics, studying the foundations of quantum mechanics. Not a lot of people were thinking about that problem. And so I did not manage to find a way to study foundations of quantum mechanics in grad school. I started out actually as an experimental high-energy physicist. And then after a year of doing that, I realized that I would rather be following my passion. And so I had to make a very difficult choice because at the time it seemed really clear that there probably wasn't a job at the end of it. If I did a PhD on the foundations of quantum mechanics, that could very well end my career in physics. But I didn't really want to spend 5 years doing something that I wasn't interested in. So I sort of made my peace with it, and I sort of gave myself permission to do what I wanted for 5 years, thinking, well, and then we'll just see. And it turned out I was very fortunate because right when I was graduating from my PhD, Perimeter Institute opened, and they were looking for postdoctoral fellows who had expertise in the foundations of quantum mechanics, and very few people in the world had decided to take that risk on their careers. So there wasn't a lot of competition. So I think other people who make that plunge maybe are less lucky. I got lucky. But it is true that if you do something that is unconventional, you will also be faced with much less competition. And you have an opportunity for seeing things that haven't been seen by others because so few others have thought about that question.
Terrific. Here, a question in the theater.
So regarding the fine-tuned action at a distance, as you called it, might there be any way to leverage that to do computation? You could set up an experiment so that in order for nature will have to prevent you from catching it in the act of sending a signal faster than light. It has to do a calculation on your behalf.
So you're saying try to make it so that if it wants to mask this causal influence and not allow signaling, then it has to do a computation to achieve that masking.
Right.
It's a good question. Yeah, I don't know offhand whether there's any clever way of making that happen. I mean, this is not answering your question, but I had a related thought about this, which is that often people worry about a different kind of loophole to Bell's theorem, which is that maybe the setting values are not really chosen independently at random, but they're determined by some influence in the past. So this requires you to think that maybe we don't have free will, for example, that things are really determined. But if you decide to make the choice of what setting you're going to use over here on the right, the result of a very lengthy computation, then the hypothesis that the setting over on the other side knows what I've done here, requires you to say, well, that computation was also done on the other side. Somehow, in a hidden way, that computation was done at the level of the hidden variables. So like a glorified version of this would be, take some binary digit of the DNA expression of some organism on a planet that's evolved for 4 billion years as your setting, right? And now that that's a pretty elaborate computation, 4 billion years of evolution to get to that DNA sequence. And is it really plausible that the hidden variables are quietly doing that computation outside of our view? I think it's not.
Okay, thanks.
Let's finish with one last question from the online folks. The question is this: is it safe to say that we humans typically introduce causal interactions because we have preconceived notions, whether we realize it or not? I think this goes to your philosophy more than your physics.
Well, in fact, I would say that in our day-to-day lives, what we're quite good at is reasoning causally, and what we're quite bad at is reasoning in a Bayesian kind of way. So we're not very good in calculating Bayesian inversions of probability. So we often make mistakes about in gambling situations. We'll get it wrong, but we're very accurate at estimating what's causing what. And in science, it's sort of the opposite. That in science, we started out having a very formal description of statistics, and we understood Bayesian inference. And for many, many years, we did not have any formalism for talking about causal structure. That statistics proceeded for many years without any notion of cause, except in the text that comes after the equations to do with the correlations. But things have changed in recent years. So Judea Pearl, for example, is a guy who has championed the notion of causal structure. He's written a textbook about it. And now we have a good formalism for how to reason about causation. I told you a little bit about it today. But I think in a way science is kind of only now getting some formalism for the stuff that we're actually pretty intuitively good at.
Very good. Ladies and gentlemen, Dr. Rob Spekkens.